The broadcast is now starting. All attendees are in listen-only mode.
Thank you for joining us today. Today's webinar will be recorded, and we will send a link to the webinar recording as well as to the slides from today's presentation following the webinar. You should receive those within 24 hours. If you have any questions, please submit those in the Questions tab in the Go to Webinar console. And with that, I will introduce our speaker today. Dennis will talk about 5 ways to accelerate and scale out Postgres. Dennis?
Yeah, thanks, Terry. Thanks for the introduction. Thanks, everybody, for attending this conversation today. And we'd like to dedicate this time to review and explore 5 or so ways to accelerate and scale out our Postgres database-based solutions. For those who don't know me, I'm a member of Apache Ignite community. I'm a Apache Ignite committer and PMC chair, and at the same time, I'm a vice president of product management and GridGain. Okay, let's move on with our agenda. So the agenda basically split into 3 primary categories. First of all, we are going to review at the most straightforward ways available for Postgres to accelerate its workloads. We are going to see how to tap into RAM with basic and standard and proven caching techniques. After that, we will slide a little bit into a different direction, checking how sharding or different replication solutions available for Postgres can kind of help to enable horizontal scalability for the database. And finally, topic, and I'll spend most of the time with that section as long as my experience falls in memory data grids and memory computing in Apache Ignite. We are going to see how caching can be amalgamated with horizontal scalability to boost performance of our Postgres deployments. So by the end of the presentation, you will have a very, very well-defined framework of solutions and techniques available for Postgres acceleration. And Apache Ignite and PostgreSQL-XL and other solutions will be among those. And for sure, also, we'll end our conversation with a quick and short demo demonstrating how Ignite can be deployed on top of Postgres within the first kind of 5 or 10 minutes. Let's move on and review the first and basic caching techniques. Here is, before we start checking those approaches, let's try to understand and kind of think for a moment, what's the ultimate purpose of caching? And basically, the ultimate purpose of caching is to speed up operations of our services and applications by reducing disk access and computations. For instance, when it comes to the computations, we'd like to minimize our CPU cycles, right? That can be exhaustive. And disk access is highlighted here for a reason. If we check this table, and that table I think was pretty famous a year or so ago, as long as it shows how some actual latency of CPU cycles, so level 1 cache access, can be translated to the more apprehensible latency at human scale. For instance, this table, what it does, if to assume that 4 nanoseconds, which is the time taken for one CPU cycle, I don't know what's the architecture, but let's assume 4 nanoseconds is how much time it takes to execute one CPU cycle. If that unit is equal to 1 second at human scale, that we are getting pretty comprehensible and easy to grasp framework. We can see that all the CPU cycles and level 1, 2, 3 cache access are extremely fast, right? They fall in the range of seconds, except for level 3 cache. Then the next fastest memory that is available for our application is main memory, RAM. It's still in nanoseconds range, and it can be defined in minutes, right? We can measure it in minutes at human scale. Surprisingly, Intel Optane dataset DC persistent memory technology also falls into the category of pretty fast memory, right? It's not that far from RAM access. But look what happens as once you get to the disk, once you get to SSDs, rotational disk, or even to non-volatile memory SSDs available or provided by Intel and other vendors. Once you are getting into the microseconds or milliseconds ranges, it will be kind of transformed to the ranges of hours and days at our human scale. And that's why caching is so invaluable and prominent for our applications and for Postgres-based deployments. Because with the help of caching, we can reduce the latency from hours to minutes, if to judge by the human scale. So let's explore what are the techniques available for our Postgres database deployments. If to start from the basics, the very first approach is a straightforward caching of our queries result sets. Let's say we have thousands of queries running, and Postgres or our applications or some other frameworks can be used to cache those result sets. So that, let's say, if you're running the same query several times in a row, you don't need to put pressure on your database. You can rather get the latest result that is cached in memory. But here is, for instance, we have a drawback. If your data is being updated frequently, then all of those caches and cached results can be invalidated, and the whole purpose of the solution can be minimal, or you might have no effect in general. So I'm not sure. I do believe that this caching technique is still used a lot, and there are some of the solutions and frameworks available, but that's probably something that would use widely during the time when the kind of web applications were deployed and developed massively. Another approach that is available in Postgres and other relational databases is caching of your execution plans. Depending on a query complexity, it might be time-consuming for your execution planner to come up with the best plan for your query. That's why if you're dealing with such a complex query, the engine can spend, during the first run, the engine can, estimate and prepare that execution plan. But once the plan is prepared, it can be reused for further queries, similar queries. And again, here is, that's something standard. It's available. Usually it's enabled by Postgres by default. And you might need to follow some of the development techniques to ensure that you are tapping into the query plans preparation. And the final thing, and that's is with the most interest for us, is caching of the relation. Under the relation, here is we assume data and indexes. So for the relation caching in Postgres, basically we have two major options available. I was trying to look if there are anything else, but probably that's it, what you have, and you most likely don't need anything else. The first one is Postgres shared buffer cache. That's a region of memory that is being allocated by Postgres on a given machine when you have your database deployed, and that region of memory is fully managed by the database. Postgres keeps data of your tables and indexes in RAM to speed up your access, right? So that your queries can be executed, so that you don't need to go to disk all the times. And that solution works pretty well, right? Especially if you can fit all your data sets on one single machine and you don't need to scale. At the same time, you know that all the modern operating systems, including Linux, FreeBSD, macOS, etc., Windows, they support so-called operating system buffers or page cache. Buffer cache. There are many names for that caching technique, but the principle is always the same. Your operating system will use part of your RAM available, a part of your RAM to cache chunks of files right in RAM. So let's say that you have your Postgres database. The data is stored on disk in files. Postgres accesses those files whenever is needed, reads or writes pages, so that chunk of data that is being exchanged is called pages, and all of those pages automatically can be cached by operating system in RAM. The more RAM you have, the more pages you can the more pages operating system can cache, and the faster your performance can be. So, but what's the difference, right? What's the difference between Postgres shared buffer cache or operating system buffers? Generally speaking, I personally didn't find any specific rule of thumb, and I would say that there is no any silver bullet. It all falls into specific use case. It's up to you. According to different observations and depending on the use case, you might want to use Postgres shared buffers or operating system buffers. It all comes to your workloads and to the way how you tune the first or the second. But also at the same time, what are the things to consider? If you enable, and if you by default you have operating system buffer cache enabled on your machine, because it will not only be used for Postgres, it will be used for any other dozens or hundreds of applications and services running on your, let's say, Linux environment. And if you have that operating system buffer cache enabled there and you activate Postgres shared buffer, then keep in mind that if you update anything in Postgres, then that update will touch both Postgres shared buffer cache, operating system buffer cache, and only after some point in time, operating system will write the changes to disk. So it means that there are possible data duplication and extra update cycles if you have both options enabled. That's one of the things to consider. So that's why if you enable Postgres shared cache, ensure that you tuned very well your operating system buffers. Another thing is that this solution is ideal, especially if you just have your Postgres database running, you don't need anything complex, you just have enough RAM available on your machine, and you'd like to tap into the RAM to boost some of the performance, to get some performance boost. But keep in mind that your caching capabilities here are limited by the RAM capacity, and keep in mind that RAM is needed not only for your kind of caching needs. RAM is needed for all of the applications and services running in the same machine. So if your RAM is overutilized, you can kick off swapping activities, and that can drastically drop down the performance. So but still, keep this as the simplest option to start with, especially if there is enough RAM space and you don't need to scale Postgres. But what if we are not satisfied with our single node or single machine Postgres deployment? What if our workloads grow, right? And our Postgres database starts choking. The memory no longer helps because you cannot beat the laws of physics, and your single machine doesn't have enough CPUs, etc., and other resources to process ever-growing requests. Let's review some of the horizontal scalability options, what we might need to consider for Postgres. But before we do that, let's try to define some of the requirements. We don't want to review all the available options. If you go to the Postgres official wiki pages, you can find that there might be, around a dozen of different solutions for that can enable some sort of high availability for Postgres. We want our solutions that we're going to review take into considerations that strong consistency is still prominent. Postgres is being widely used for operational workloads. And if you scale Postgres somehow, we are not ready to sacrifice consistency. Even if Postgres is somehow became scalable, we'd like all of our transactions to stay consistent across for the entire solution. Also, if we enable that horizontal scalability for our database, we want to be sure that we are getting load balancing benefits. We don't want one instance of our Postgres database to process most of the queries. Otherwise, there is no any sense. We don't want to have underutilized machines. We'd like the solution to load balance requests. We'd like to get equally loaded solution. And high availability and failover is also should be a reasonable requirement. As long as it's all simple when you have single node, single machine deployment. But once you start distributing or coming up with some horizontal solution, here is you need to consider that there are more dependencies in such a configuration, and we want such a solution configuration to be highly available and to support failover. So what are the options? Let me introduce some of them. Probably the most famous ones. The first one is Pgpool 2 component. That is a pretty good solution for read-heavy workloads. So if you take a look at this architecture, you'll see that the primary components are for sure your application that like to get data from this relational database. Also, we have Pgpool 2 coordinator. You can have a kind of a replica of the same coordinator to ensure and enforce high availability and failover. And then you have primary replica of your Postgres database, and you can have 2 or more secondary replicas. All the replicas with this architecture, the goal is to improve your read-heavy workloads, and coordinator helps to load balance all the queries coming from your application, with the goal to ensure that not only the primary replica is under the load, but the load can be distributed across all of their Postgres instances available. And here is, again, suggestions and considerations. Yep, if your use case is read heavy, you can keep all the data on one single machine and you just want to load balance your request much better. Have a look at Pgpool 2 solution. Also, if ACID consistency is required for your use case, which should be the case for most of the scenarios, then you can enable synchronous replication between your primary copy and standby copies. But here is only one note to keep in mind. If the replication between primary and secondary, so standbys, is synchronous, then you can drastically reduce performance of your write operations, because the more replicas you have, the longer will be your write operation for the synchronous replication, because you need to update the primary copy and also you need to wait while all the replicas get updated. But anyway, it's available, right? But another solution why this might not work for all their use cases, and it's not a silver bullet again, is that your primary machine capacity, your primary replica capacity defines your total cluster capacity for the data generated by the application. If to put it simply, let's say that your total cluster capacity, you have 3 different replicas, primary and 2 backups, 2 standbys. And if each machine goes with 2 terabytes of RAM or disk space, doesn't matter. You have 6 terabytes of disk available in total. But your primary machine has only 2 terabytes, and you cannot store more than 2 terabytes of unique data generated by your application, because the rest of 4 terabytes are used as a replica, right? And let's say that one day your application now needs to store 2 terabytes and 10 megabytes, so 100 megabytes of data. What do you need to do to accomplish that? Right, you need to shut down your primary Postgres cluster. You need to migrate Postgres database to the machine with probably 3 terabytes or 2 terabytes and a half. And after that, you will be repeating the same procedure again and again. So here is, consider this. If your use case is read heavy and you are not projecting that your application is going to generate a lot of data in the foreseeable future, then you can use Pgpool 2. If, let's say, the chances are high that you will be required, to migrate your Postgres primaries to more advanced machines again and again, then let's review other use cases. The other use case actually solves a problem related to their total available space total disk space or memory space available for our applications. And also it helps us to support not only read-heavy workloads, but also mixed workloads, so write-intensive workloads. There are several solutions. The most known one are PostgreSQL-XL, Citus data, and also I know that Azure supports, Microsoft Azure supports a distributed and sharded Postgres, and that solution is based on Citus data, and that company, if not mistaken, was acquired by Microsoft some time ago. So, but from the architecture standpoint, all of those solutions are pretty much the same. Your Postgres, you no longer have, just primary replica and standby, so backups that keep the same data sets as it happens with Pgpool 2. Here is all your data is sharded or partitioned across a cluster of data nodes, across a cluster of machines. And if we take the same example, let's say that I have 3 data nodes, and each data node goes with 2 terabytes of disk space. It means that in total I will have 6 terabytes for my application available, and we can tap into all of those 6 terabytes. Yes, you might, dedicate some disk space for backups, right? I mean that as long as the solution is distributed and you want to support high availability and failover, then yes, let's say for each record that you store in such a distributed solution, you can have a backup copy, which means that, if your application generates 3 terabytes of data, then you can use the rest of the 3 terabytes as a backup copy. But if you need to scale out, you can scale out much more easily, right? You just add new data nodes to this configuration. Suggestions and considerations. If in comparison to Postgres Pgpool, this solution is suited for mixed workloads, but that's not the same Postgres. Even though the community is trying to ensure that PostgreSQL is fully compliant with Postgres syntax, it's still the work is going, right. It's incompleted. But anyway, you need to do some migration, but it might be worthwhile. Total capacity, as I explained, of your class, total disk space that is available for your applications is defined by your total cluster capacity. So you have 3 machines with 6 terabytes. All of those 6 terabytes are available to you. You would like to scale to 10 terabytes, you will be able to do that. Scaling a failover, it's possible, but there are some of the procedures that might involve maintenance windows, but that goes out of scope of this discussion. You can review it if this configuration is good for you. And it would be, everything would be perfect, right? But still, even this solution, PostgreSQL or Citus data, etc., they do not cover all of the use cases where Postgres is presented, as long as still these solutions are disk-based. And if you remember our table that compares access latency of memory to disk, still here as we are not tapping in RAM. Yes, you can enable operating system buffers, etc., but those operating system buffers will be enabled per each node individually. There is nothing shared storage, and it will be hard to coordinate, hard to maintain, etc., globally across a cluster of machines. That's why the next topic of this conversation is for those who would like to combine both horizontal scalability, preserve Postgres, and also reduce latency by enabling RAM access across a cluster. Let's review in-memory data grids. And as long as my expertise is related to Apache Ignite and GridGain, I'm going to review those solutions. But as always, you can find the research for other in-memory data grids options. Apache Ignite and GridGain, right? A quick overview. So the 2 primary components of this platform are the storage or a set of the APIs available for the storage. When it comes to the storage, your memory is used can be used and is used as your primary storage. It doesn't matter, you have 2 machines, 3 machines, 5 machines, 10 or hundreds, etc. all the RAM space available across the cluster of machines can be seen by your applications as one database, as one cluster. When it comes to the persistence layer, again, Ignite comes with its own persistence, but that's not the topic of our today's presentation. And Postgres can be used as persistence, right? And Postgres here is, we believe that you have Postgres deployed, you'd like to accelerate it, you'd like to tap into RAM, you'd like to add horizontal scalability, you are taking and deploying Ignite on top of Postgres database, and you are achieving horizontal scalability through that in-memory storage. Postgres stays as your backup, permanent, durable storage, but all of the workloads, primary workloads, are handled by Ignite, and Ignite ensures that Postgres stays in sync. So the storage is the first, right, component of Ignite. On top of the storage, we have a variety of APIs. Let it be key value, SQL, transactions, different compute grid calculations. We're going to review it. Everything that you see in red is available in Apache Ignite, in open source. What you see to the right and to the left of this slide is being provided by GridGain on top of Ignite. If you need data center replication, security, running upgrades, etc., you can migrate your Apache Ignite deployments to GridGain. And so that you have a complete understanding of two primary use cases of Ignite and GridGain deployments, let's quickly check in this slide. First of all, if we have Postgres, right, we don't want to disrupt our existing application. We don't want to disrupt our existing architecture. We'd like to enable horizontal scalability and have a distributed, truly scalable memory storage, but we don't want to sacrifice what we achieved so far. We'd like to we prefer to keep Postgres in our architecture and experiment enabling memory computing on top. And that's what you can do with a memory data grid as a deployment option. Ignite GridGain is deployed on top of Postgres, and your application can switch and work with us directly. Another use case that you can review afterwards is when persistence is available and provided by Ignite and GridGain. You just enable our persistence, and your whole data set now will be distributed across memory and disk. But that's something that is good for greenfield application and not a topic of our today conversation. So how Postgres is accelerated? Let's check it out. If you remember with Pgpool solutions, you use the same Postgres, but you need to deploy several replicas, and Pgpool 2 handles all the requests, and that's good for read-intensive applications. With PostgreSQL, you still deploying a solution developed by Postgres community, and that supports Postgres APIs, etc. But there you're truly tapping into the distributed nature of the solution. Your data can be sharded, you can usefully exploit all the disk space available for you. There are some other required operations for the scalability, etc. But overall, that's a good scalable solution based on disk. With Ignite in GridGain, the concept of partitioning and sharding is pretty much the same as with PostgreSQL. The only difference is that you do this right in memory. If you have terabytes of RAM or gigabytes of RAM, you can use all that RAM space available for you to make your performance much faster, to reduce your access latency significantly. So here is with Ignite, what happens? Let's say you have your applications that do some key value updates or SQL queries. You can switch. A recommended way is just to switch your applications to your Ignite or GridGain cluster. All the data will be distributed. If you need to store, let's say if you started with 100 gigabytes of data, then you need to scale to terabytes. You just easily scale out your cluster, one extra operation. Ignite and GridGain will be processing and serving all the queries, taking data right from RAM. And remember that table that compares access latency. Instead of kind of minutes or hours, if to judge by human, by the latency, how we perceive it as humans. Here is we can do this in seconds, if to take the same human scale. But at the same time, we want to ensure that Postgres stays up and running, and that we can use it as a backup storage, as external storage, and Postgres might be still accessed by some other applications. Ignite and GridGain, they can write through all the changes to disk to Postgres. Let's say any record gets updated in Ignite, you can write it down back to Postgres. And you can do this synchronously or asynchronously, depending on your use cases. When it comes to the SQL, Ignite and GridGain SQL is not Postgres compliant, but it fully supports NC99 specification. So all the basic and standard queries, selects, updates, insert, joins, order bys, groups, etc., everything is available. Yes, some Postgres-specific syntax is not available, but that was never a big deal for those who were accelerating Postgres with Ignite and GridGain. And here is when it comes to the indexes, in addition to data in memory, we also can store indexes. So when you run distributed queries, SQL queries with Ignite, all the data that is stored on a specific node will have a subset of a B+3 stored on the same node, which means that you have a B+3 split across a cluster of your machines, and whenever you run complex queries with joins, they still will be executed in a fast way, because all the indexes are available, all the needed indexes are available on each node that stores a subset of the data. But let's quickly check how we can ensure that collocated queries or queries with joins can be supported without any performance drawbacks. And this, here is I would like to briefly touch upon Affinity collocation concept. And the same concept, it's not a brainchild of Ignite or GridGain. That's something that became a general practice for many distributed databases, not only in memory databases. Here, as you can recall, Google Spanner, different cloud databases. It can be MemSQL, OldDB. Many solutions tap into this concept to enforce efficient distributed joins. So the idea with Affinity collocation is that, as with relational databases, we can use foreign keys to enforce data integrity between our several relations. Let's say you have countries and cities. And for the cities table, you can say that country ID column will be my foreign key to ensure that whenever you insert in your city, in your country, that city will be added only if this country exists, right, in the database. But a pretty similar concept is slightly changed but reused for the distributed world, for Ignite. But we call it Affinity collocation. Let's say that you have the same tables, countries and cities. And if you want to run efficient joins, let's say joining data of countries and cities tables, then you had better to ensure that all the cities of the same country are located on a specific cluster machine, like it's shown on this picture, where Canada, all the Canadian cities are located on the node that stores a record of Canada. And the same is true for India cities, but those are stored on another machine. And when you're defining your city table, there, instead of a foreign key, you just need to tell that country ID will be my affinity key. And right after that, when your application will be inserting data into the cluster, Ignite internally will take the value of your country ID column, because that's the affinity key, and will calculate a destination node where that record has to be stored. And here is, if you just imagine for a second, as long as all the cities that belong to a specific country, like Canada, have the same country ID, when you will be inserting all those cities into the cluster, they will be going to the same cluster node. And after that, you can run complex joins that join data in Canada, let's say all the Canadian cities, etc. And you can do this efficiently, avoiding any data shuffling over between the cluster nodes. At the same time, this technique helps us to run collocated computations and reduce network traffic. Because one of the golden rules that we need to remember about in memory computing and about distributed systems is that it's not enough to, sometimes it's not enough to put data in RAM and to expect, order of magnitude performance improvements. It's also, our goal is of architects and engineers is to design the system in such a way so that we can tap into the Affinity collocation, and then we can make use of collocated computations. Because SQL is great, right? SQL is good and it's good language, but it pulls data from your storage. It will be transferring with your distributed solution. It will be transferring the data constantly from your server side, from your cluster side, putting your network on pressure. Network is slow, right? But if instead you can come up with a way how to wrap your code into a computation and send it to for the execution to your cluster, then you can eliminate network. And once the network eliminated, you can tap into the full potential of your RAM. No any data transfer, no any data shuffling. You just send your execution computation to the cluster. It gets executed locally across a cluster of machines, and you're just getting the result set. And that's how you can usually expect an order of magnitudes performance boost when you use both RAM and collocated computations, eliminating or reducing network traffic. And this example shows that, let's say, we set up our Affinity collocation. We now have, whenever we are inserting data into the cluster, all our cities will be distributed based on the value of their country code or the country ID. And if you take this example that tries to count all the cities that are located in Canada and India, yes, this query will be sent from your application, but then it will be executed on each node individually. Each node completes its part, and it will transfer back the result sets to your application. And then internally, Ignite, part of Ignite that is running on your application side, will reduce that query, will prepare a final result set for you and return to your application level. Compute grid, that's actually the life without stored procedures. In the relational world, including Postgres, we use stored procedures heavily when we'd like to minimize or eliminate network usage. Compute grid, you can see compute APIs as a more advanced way of for your computations. The stored procedures, we are limited by the syntax and capabilities of SQL. With compute grid, depending on our programming language, we can use all the APIs of Java, .NET, C++ available for us. That's true for Ignite. Let's say that here is, I can give you a really quick example. One of Ignite users, that's a large bank, they were accelerating an Oracle database, and they were storing millions of savings accounts in that Oracle database. Once a month, they needed to traverse all of those savings accounts, do some calculations, and apply a final interest rate. And they would start an application that would, late night, once a month, connect to the Oracle database, use SQL to select all those saving accounts, do some computation locally, apply the interest rate, and write all the changes back to the database. It was taking that application more than 2 hours to complete the procedure, because the bank has like more than 100 million savings accounts. Once they migrated to Apache Ignite, once it was deployed, right, as a memory cluster, yes, they stored data in memory. They started using our SQL and other key value APIs, but still, yes, they were getting much better numbers. I think it was taking like around an hour to complete the same procedure because the data was in RAM, but still it was taking hours, right? Not 2 hours, but still like 1 hour and something. And after that, they reviewed the capabilities of compute grid. What they did, instead of sending all that, executing all that SQL from the application, and they developed a Java compute task, and that compute task was distributed across all the cluster machines available in the cluster, and that compute code was executed locally on each machine. And after the compute code was completed on every machine, each machine would send back a partial result set that was, eventually reduced by your application. And with that approach, there was no any data like network utilization. And after this optimization, it took them, like 10 or 15 minutes to complete the same computation, because they could amalgamate both RAM and eliminate and collocated computations. They eliminated heavyweight network utilization, and they store data in memory. That's also what you can do. You can think of and come up with some other use cases when you have some advanced computations, and if you can run them on their server end, on your cluster end, that's Ignite for you. You can use Java.NET and C++ and Ignite. And when it comes to transactions, as long as yes, PostgreSQL-XL, Pgpool 2 enables consistency, enables ACID. With Ignite, you also have full support for ACID transactions. Ignite supports two-phase commit protocol, and whenever you are completing your distributed transaction, Ignite ensures that Postgres stays consistent. Let's see how it happens. Let's say you have your application, right, and you are updating several records, reading, updating that was stored across several tables in Ignite, and Postgres is interconnected with Ignite cluster in this case. And then your application finally executes that command transaction commit. What happens afterwards? Your coordinator, which is your application in most of the scenarios, will write to their database, to Postgres first, and only after Postgres responds successfully, the transaction will be committed in Ignite. Here is for sure our two-phase commit protocol ensures that failures can happen during this transaction commit. Postgres can go down, or one of the Ignite nodes can, shut down, etc. Many things can happen. But if you'd like to see how all of those corner cases and failure scenarios are resolved, just go and read more about our two-phase commit implementation in their specially created documentation and blog post. But generally it works, and that's why, even though Ignite can be deployed as a memory option on top, you still can run distributed transactions, which is essential for many Postgres-based deployments. Okay, let's quickly run one demo. So the goal of this demo is not to show you performance benefits of deploying Ignite. That's something that you can explore later, but to show you how it's easy to start with Ignite and deploy it on top of Postgres if you are doing your first steps in memory computing and you're experimenting with Ignite. Let's set this task. Let's assume that you have a Postgres database running in your development environment, such as this laptop. I have it on my machine. So I have a simple database, cities, countries, and country language that I took from Postgres website and deployed here, so we can see what's inside. Here there is some cities. We are going to experiment with this data. And now I want to deploy Ignite on top. What can I do? Yes, you can create a custom Ignite configuration following best practices and to ensure that all Ignite tables, caches are connected with Postgres tables, and whenever anything gets updated, Postgres will stay in sync. But also here is we have a simpler approach. We can go to console gridgain.com web console. That's a free tool for management and monitoring that can be used for both Ignite and GridGain. It doesn't matter what you use, just go ahead and download it, install on your premises. I am going to use a hosted version that is already deployed and available for this demo. What I want to do, this tool goes with this feature. I can connect to a relational database, such as Postgres, and import its schema. So that's my Postgres database. I'm connecting. I want to import this public schema. Okay, load it. So we have only these three tables. It's all true. No cheating. And next, what happens? Save. Save. What happened after I just clicked on the save button? This tool connected to Postgres, read the schema tables, and converted it into the Ignite specific configuration. So here is, if we go through this configuration, you will find many parameters for every Postgres table. Ignite created a dedicated cache, and all this configuration is prepared. What I will do, I will just go ahead and save and download this. I don't want to do any changes. After it's downloaded, you can unzip it and start using this configuration. But at the same time, I did the same procedure before this session. So let me just show you how this project looks like. I don't want to spend too much time in this. Yeah, I forgot to start my IntelliJ IDEA environment. Give me a second. By some reason, yes, looks like IntelliJ IDEA shut down itself. All right, so that's the project. I just created identical project before this session. I'll show you what I changed after I downloaded it from Web Console. Come on, Lord. So here's what goes inside of this project once you download it and unzip. I changed this file only. So here is, I again instructed Ignite to use this connection URL to access my Postgres deployment. And also the tool Web Console prepared this configuration for us. For instance, here is you can find these placeholders that will be used by Ignite nodes to connect to Postgres. And here is we are using their actual values. And then here is some of the Ignite specific settings. We're not going to look into them, like which cache, some of the parameters that this complex conversion is needed to ensure that Postgres will be updated without any issues, etc. But all of that was prepared automatically for us. Also, the tool generated some of the code samples. For instance, I can use this code to start my server node. I don't need to request an IT department to deploy an Ignite cluster in company's infrastructure or on a cloud. I can start developing code right from my laptop. I don't need anything. Okay, the first node is started. The server node is going to store the data. Let me start another one. Even on my local machine, I'd like to have a distributed cluster. That cluster will go with 2 Ignite server nodes. All right, come up. It's ready. Now again, we can go back to this tool, to the monitoring tab. I'd like to see that the tool can connect to their cluster. Yeah, so this tool that is running somewhere in the cloud now connected to my local cluster. And here are my 2 nodes. They're running just 1 minute. The uptime not that much. And we created, once I started those nodes with the default configuration generated by the same tool, I can see that these caches were created in the clusters, but they're empty. So let's carry on with the next step. The next step would be to use this code template, again, generated by Web Console. So what happens here, let me start in first, and then I will guide you through the source code while the data is loading. So this application, this simple Java application, will connect to this cluster of 2 nodes, and it will load data for every table. But where will the data come from? It will go from Postgres. So here is the application just executes load cache method. And as long as in the configuration we already have Postgres and Ignite interconnected, actually Ignite will issue a special request for all of those 2 server nodes to go to Postgres and pull data from disk into memory. So according to the application it's completed, so it says that the data was preloaded from Postgres to Ignite. Let's go and check it. Right, yes, we have the data in memory. Only primary copies, we are not storing any backup copy, but it can be improved easily. What next, right? Let's assume that we have some of the queries prepared. We'd like to experiment with our in-memory cluster. And that's Ignite SQL. That's the syntax supported by Apache Ignite. For instance, we can use this operation to find the most populated countries in the world. And this query goes right to Ignite. It doesn't go to Postgres. All the data is in memory, and we execute this right in RAM across those two machines. So the answer is as follows: China, India, and United States share the first three ranked as the top three countries in the world. Now, what if we run a more advanced query with data with joins? So here is we are trying to see the most populated or inhabited cities in countries such as United States, Russia, and China. Let's run this query. Let's see what would be the response time. Yeah, so by some reason it takes a lot of time. I think that's because my the tool is deployed in the cloud, and from the cloud it needs to go to my local machines through the many network endpoints. So disregard this performance. I think it just caused by the way how my development environment looks like. But generally, we could complete this join, and that's the result set. Shanghai, Moscow, New York are the top three cities in these three countries. Next, let's do some updates. All right, we can read data from Ignite with SQL in memory, distributed, it's all right, but how can I ensure that the data stays in sync between Postgres and Ignite cluster? All right, so let's assume that we have this city, right? And that's the city's population. Now what I want to do, I would like to change the population from more than 200,000 to 5,000. I'm executing this operation. This operation gets executed in Ignite. So we need to rerun this query. Yes, and we see that this record was changed in Ignite. But what's about Postgres? Let's go back to Postgres console. You remember that before the demo, I executed the same query, identical, and that was the population. Now, if I rerun this query, you can see that the population was changed. Ignite automatically changed this. We, as application developers, don't need to go to both Ignite and Postgres and keep those databases in sync. And that can be a transaction, right? You can just run a distributed transaction, and you can be assured that the changes will be transactionally completed across Postgres and Ignite. And finally, if I do delete, let me delete this record, the same record. It's deleted in Ignite. Let's double check it. Yes, the record is deleted. How about Postgres? Yeah, it no longer exists in Postgres. So that's how simple it is. I think that it took us how much time? Probably 10 minutes to import schema from Postgres, convert Postgres tables to Postgres configuration to an Ignite specific configuration, deploy Ignite on top of Postgres database, and run some simple queries that demonstrate that you can use the same SQL APIs to read data from Ignite, and whenever you update, do any changes in Postgres will be updated as well. All right. And we have two final slides left. First of all, if any of you is curious about open source, is willing to contribute to open source, would like to, build or become more skillful in distributed systems and ready to contribute, we are waiting for you. So come to Apache Ignite community, and you can learn how to build distributed systems, storages, computation, SQL, machine learning, etc. There are so many ways how you can, improve your technical skills if you contribute to Ignite. So just please welcome. If you just would like to use Ignite, absolutely do this, and don't hesitate sharing feedback with us, with the community, because with your help, we will be able to improve Ignite for not only for you but for the others. And Ignite, if you are hearing about Ignite for the first time, here Ignite is one of the top 5 projects in Apache Software Foundation. In 2 categories, we are the second most active project among the dev list community. There are a lot of discussions on the dev list, And also we are the third most active project within the user list community. So all the users, there are so many users that are using Ignite that many questions are being asked, and Ignite community is trying all the best to get them answered and improve the product. So whether you are on the user side or a developer side, please come and use one of the top 5 projects of Apache Foundation. Contribute to it or try to experiment it, and hopefully you will be able to accelerate your Postgres database deployments, and this will be helpful. But as a summary, again, yeah, the purpose of this presentation is not to pitch Ignite only. Ignite here is, again, is one of the viable options that will help you to accelerate Postgres deployments. But if standard basic operating system caching is needed, you don't need to scale, or you just need Pgpool 2 for read extensive deployments, then take whatever is relevant for you. But keep in mind that, yeah, if at some point of time you need some scalable in-memory solution that provides both horizontal scalability and use RAM as a distributed storage, then Ignite always can be seen as an option for your Postgres deployments. So having said that, thanks for coming. And if you have any questions, I would be happy to answer them.
Yes, thank you, Dennis. Again, if you have any questions, please enter them in the questions panel in the GoToWebinar control panel. We have a question. Dennis, is there any limitation on which versions of Postgres you can use this with?
No, we are not aware of any limitations. So how this whole integration works, we are just taking a Postgres JDBC driver. If you're using the latest version of Postgres or an old one, then you just need to download the right JDBC driver from the Postgres website and set it for Ignite. For instance, my Postgres version, I think it's not the latest, it's 9.6. And I think that I downloaded this driver more than a year ago. And I do believe that right now, if you take another version, you just need to take another driver. This integration is based on JDBC.
Okay. And another question, is it possible to access more than one Postgres database if there's multiple databases that you'd like to draw from?
Yeah, that's actually a perfect question. I think that next time we had to mention this as one of the advantages of Ignite as a solution. Ignite can be configured as your shared in-memory layer above several Postgres deployments. So let's say that you have 2 or 3 Postgres databases deployed. And from those 2 or 3 databases, you'd like to cache 2 tables from the first one in Ignite and let's say some 5 tables from the other database in Ignite. Yes, in your Ignite configuration, you will have several connection points to several Postgres databases and Ignite, but from the application standpoint, that will be working with Ignite, that will be just one shared memory storage, and internally that memory cluster of Ignite nodes will be going to separate Postgres databases and will keep them in sync. Only one point with transactions, right? If you are running a transaction, then you need to ensure that, and you need ACID transaction guarantees. Then a single distributed transaction need to work with one Postgres database. Yes, we can commit to Postgres consistently, but we cannot in parallel commit consistently across several Postgres instances. So here is for the transaction one remark. Your distributed transaction that you run in Ignite need to use those tables stored in Ignite that are caching data from one Postgres instance. If you use several tables in Ignite that cache data from more than one Postgres instances, then we cannot we cannot guarantee strong consistency for all the Postgres databases that are deployed beyond Ignite.
Okay, very good. Thanks everyone for attending. We're at the top of the hour now, and we will send a link to the slides and the video from today's presentation within the next 24 hours. So please watch for those in your inbox, and please pass the video recording, the webinar recording along to your colleagues if they would find it helpful. Thanks everyone, and have a good day.